Good morning, class. Here's chapter 5, integrals. We're going to cover from 5.1 to 5.3 here, known as the fundamental theorem of calculus, or short, FTC. So in this chapter, we cover FTC and the substitution rule. Excuse me. So, reminding everyone how we came up with the basic integration formulas. If the derivative of kx is k, the integral of k dx must be kx plus c. That's, excuse me. The power rule, the derivative of x to the power of n is n x to the power of n minus 1, then the integral of x to the power of n must be 1 over n plus 1 x to the power of n plus 1 and a constant. And we went over that two different ways. One way is, notice the differentiation, we multiply by n and we subtract 1 from the exponent n. In the integration case must be the reverse process going that way. So first subtraction becomes addition, second multiplication becomes division. Also, we looked at the derivative of the right side and we proved it's x to the power. The rest of it. If the derivative of e to the power of x is x, the integral of e to the power of x dx must be e to the power of x and a constant. ln x, the derivative is 1 over x, the integral must be, the integral of course 1 over x dx must be a natural log and a constant. And the rest of them follows in the same manner. Tangent, for example, if the derivative is secant squared, then the integral of secant squared dx must be tan x and a constant. And the rest of them follow in the same manner. And these two, just the same as differentiation, we do them step by step. If there's a constant, you just keep that constant. And in the case of e to the power of kx, when you differentiate, you multiply by k. So if you integrate, you have to divide by k, the integral of e to the power of kx dx. So 1 over k, e to the power of kx, and a constant. So that's what we've done. And now, sections 5.1 to 5.3, the FTC, fundamental theorem of calculus, the method of exhaustion. Areas of familiar polygons, such as triangles and rectangles, enable us to find the areas of more complicated regions by filling the region with increasingly smaller elements of known area. This is called the method of exhaustion. For example, the area of a circle, when they didn't know it was pi r squared, if we put a three-sided, a triangle in there, we can calculate the area of that, and that's an approximation. As we add to the number of sides, the polygon that we come up with represents a better approximation. And that's the same thing with the area problem. You want the area under the curve S. Find the area of the region S that lies under the curve y equals f of x from A to B. This means that S is bounded by the graph of a continuous function, y equals f of x, a continuous function, where f of x is larger than or equal to 0. This is a positive function, not negative. The vertical lines, x equals a and b, x equals a and x equals b, and the x-axis. So this, the synopsis of that is explained here. S represents every pair x comma y such that x is between a and b, y is between 0, the x-axis, and y equals f of x. Now, we cut this in so many rectangular shapes. For example, if you cut it into 4, then this width, which is delta x, is going to be b minus a over n, b minus a, in this case, over 4. So this distance, everybody, is delta x. And we make the width to be identical because it's easier to calculate. Now, what is the height? We use the Riemann sum, summation of n, summation of I going from 1 to n, f of x of I delta x, f of x of 1 times delta x, all the way to f of x of n delta x. What is that f of x of 1, f of x of n? The height. You can use the left endpoints. If I use the left endpoints as the height, everybody, this means this one, this means this one, this one, this one, and you can find this area, this area, this area. How do you find it? Delta x times the height. The first one would be f of a, and then the rest of it. If I want to use right endpoints, that works too. But remember, these are all approximations, and that's the idea. This approximation gets better as we add to the number of rectangles. Here's an example. The function f of x is positive on some interval a to b. Determine the area of the region between the function and the x-axis. Example, determine the area between the function f of x equals x squared plus 1 and the x-axis on 0 to 2. In other words, we want to determine the area of this shaded region. First of all, class, notice I'm talking about this function is y equals x squared plus 1. Okay. So we are just looking at the shaded region. So I'm going to erase my work. We are going to calculate, let's say we're going to use 4, and we're going to calculate the delta x. N is 4, delta x is b minus a over n. So we cut it into 4 pieces. B minus a over n means 2 minus 0 over 4 means 1/2 means 0.5. Okay, so what happens next? So the width is fixed and it's 0.5 or 1/2. What is the height? Well, you can use the right endpoints looking like that. Which means the width is 0.5 or 1/2. The height would be f of 0.5 for the first one, for the second one, f of 1, for the third one, f of 1.5, and the last one, f of 2. We call it R because we're going to use the right endpoints, the endpoints, okay, and 4 because n is 4. The width is fixed, delta x, which is 1/2. F of 1/2. For example, what is f of 1/2? If I put 1/2 here, I get 1/2 squared. 1/4 and 1 is 5/4. If I put 1 squared, 1 and 1, 2. If I put 3/2, square it, 9/4, and 1 is 13 over 4. If I put 2 squared, 4 and 1, 5. So I get 5/4, 2, 13/4, and 5. And by the way, you can just factor out the 1/2. So 1/2 times that. In any event, you put it into a calculator, you get an approximation 5.75. What if we use the left endpoints? We call it L4 because we are using the left endpoints with n being 4. So now we use the same delta x where the width for each one is identical, but the height would be f of 0 for the first one, f of 0.5 for the second, f of 1 for the third, and f of 1.5 for the last one. And notice this is what happens. A big chunk is identical, everybody. And so if you know that, then you calculate this part and you don't repeat it here, just put it in here. And you put it into a calculator and you get 3.75, which indicates obviously this underestimates, this overestimates, and the area is somewhere in between. Now, before we move on, one easy way to understand these points just from 0 to 2, everybody, put a line segment 0 to 2. 0 is A. The first one doesn't have to be 0, is A, and the last one is B. And delta x is 0.5, so 0.5, and then 1, and 1.5, and 2. For the right end points, everybody, for the right end points, don't use this one. Use the rest of it. Notice f of 0.5 or 1 half, f of 1, f of 3 halves, or 1.5, f of 2. For the left endpoints, don't use this one, use the rest of it. Okay, this is one easy way to see how the height or the functional value are calculated. And so let's look at the same thing and change n from 4 to 8. Delta x this time would be 2 minus 0 over 8, or 1/4, or 0.25. The right endpoints look like that. And so delta x, this is the Riemann sum. Delta x is 0.25 or 1/4 times f of 0.25 or 1/4 plus f of 2/4 or 1/2 and all the way to the end. And on purpose, I'm using 2 over 4, 3 over 4, 4 over 4. Obviously, this means 1/2. And I put it into a calculator and I'm coming up with 5.1875. I'm going to do the same thing for the left endpoints. And first and foremost, notice again, for the right endpoints, the last one is not here. For the left endpoints, the first one is not here. So that really simplifies calculation. Puts it in, and you get L8. And for n equals 8, the area is between these two numbers. When n was 4, it was between these two numbers. As you can see, the difference between these two is 2, but the difference between these two is only 1, which means the approximation is getting better. So the approximation gets better as n gets larger. And that's the idea, everybody. So the other thing I want you to notice, this function is increasing and it's concave up. When the function is increasing and concave up, right endpoints overestimate the area. Left endpoints underestimate the area, okay? That's what happens. And the graph indicates that. So you should be able to tell by the graph. The fundamental theorem of calculus. Suppose a continuous function f is defined on the interval of a to b. If the interval is divided into n subintervals so that delta x is b minus a over n, and x sub 0 is a, x sub 1 is a plus delta x sub 2 is a plus 2 delta x, all the way to the end, x sub n is a plus n delta x, which becomes the last point b. Then a Riemann sum associated with f is this following sum, the summation of I going from 1 to n, f of x sub I delta x equals f of x sub 1 times delta x plus f of x sub 2 times delta x all the way to f of x sub n times delta x, add them up. X sub I is any point in the interval of a sub I minus 1 and a sub I, meaning left endpoints, right endpoints, midpoints, anything makes no difference. It's an approximation. This represents the approximation of the area under the curve. What is the geometry and procedure? The geometry and procedure called Riemann sum. Partition the interval of A to B into a few. For example, let's say 4 subintervals. Make 4 rectangles. The width is delta x is b minus a over 4. And the heights are f of x sub 1, f of x sub 2, f of x sub 3, and f of x sub 4. These are the 4 points. Make 8 or more. As the number of rectangles increase, the approximation gets better. We can use any of them, left endpoints, right endpoints, or midpoints. The formulas you don't have to memorize. You just stick with the line segment that I mentioned. L sub n would be delta x, f of x sub 0 all the way to f of x sub n minus 1. R sub n would be delta x times f of x sub 1 all the way to f of x sub n. That means in this case, the first point A is not used for R. For this one, B is not used. Or the middle point, f of x sub 1 bar means x sub I bar is x sub I minus 1 plus x sub I divided by 2. What do we mean by that? Here's what it means, class. Okay. I'm just making up. Let's assume we cut it into so many pieces, n pieces, okay? This is A, this is B. This is x sub 0. This is x sub n, okay? So for the left end points, for all of them, delta x is b minus a over n. For the left end points, you use all these points as the functional value, put it in. You do not use b. Do not use b. For R sub n, you do not use a, the first point. What is the midpoint? You calculate the midpoint for the first point, and then you add delta x for the next one, and the next one, and the next one, and the next one. And normally that approximation is better. So left endpoints, don't use the B. Right endpoints, don't use the A. Midpoint, just those points. Functional values at those points. That's it. I'm going to erase my work. So the area is approximated by the summation of f of x sub I delta x as I goes from 1 to 4, for example. In this case, f of x sub 1 delta x plus f of x sub 2 delta x plus f of x sub 3 delta x plus f of x sub 4 delta x, if you cut it into 4 pieces. If you do 8, you have more, right? You have 8 of them. So the area under the curve is exactly equal to the limit as n approaches infinity of summation of I going from 1 to n of f of x sub I delta x, where delta x is b minus a over n and x sub I is a plus I delta x. And this limit is pretty tedious to calculate. And we take the easy way out for that one, which is one of the fundamental theorem of calculus. So for this one, we use this one, which says the integral of a to b f of x dx is capital F of b minus capital F of A. Remember, capital F prime is lowercase f. That means evaluate the antiderivative at the top and subtract from it evaluated at the bottom. That's the Riemann sum. It's a lot easier than this limit. Now, the other FTC says d dx of the integral of a to x f of t dt is f of x, meaning if you integrate and then differentiate, they undo each other, they give us the function back. Notice the lower limit is a number, the upper limit is x, this is f of t dt, so replace it. To make some sense out of what we just said, let's look at this. The integral of a to b f of x dx. This is the integration symbol. The symbol was introduced by Leibniz and is called an integral sign. It is an elongated S and was chosen because an integral is a limit of sums. Lower limit of integration, upper limit of integration. This is the integrand. Dx, variable of integration, also known as dummy variable. It is called a dummy variable because the answer does not depend on the variable chosen. The dx simply indicates that the independent variable is x. So the integral of a to b f of x dx is a number. That's why it's called the definite integral. It does not depend on x. We could use any letter in place of x without changing the value of the integral. The integral of a to b f of t dt is absolutely the same thing. Or its approximation, the integral of a to b f of x dx, is almost the summation of I going from 1 to n of f of x sub I delta x, meaning f of x sub 1 times delta x plus f of x sub 2 times delta x, all the way to the last one, f of x sub n times delta x. This sum is called a Riemann sum. The precise value would be when we take the limit a equals to the limit as n approaches infinity of summation of I going from 1 to n of f of x sub I delta x. So the area is equal to this limit, also is equal to this definite integral, and this definite integral is capital F of b minus f of a, which is a lot easier to calculate. Let's evaluate integrals using areas. The integral of 3dx from -2 to 5. So what do we mean by areas? Note, the integral of a to b f of x dx represent the area under the curve of f of x from a to b if the function is positive. Otherwise, it represents the difference of areas, known as the signed area interpretation of the definite integral. So if that is the case, let's look at the area. What is the function? The function is y equals f of x equals 3 is a horizontal line. And we know how to draw a horizontal line. From -2 to 5, from a to b, so we're going to plot over -2 to 5. Which means here's the grid, here's the function, y or f of x equals 3, it's a horizontal line. And we want to go from -2 to 5. That means we want this area. So the definite integral represents the area of a rectangle of a width 5 minus -2, this width. Which is 5 minus -2. The width is 7. And the height is 3. So, because it's a shape we are familiar with, the geometry says multiply the 2 and you get 21. Thus, the integral of a to b 3 dx, the integral from 5 minus -2 times 3 equals 21. This is a equals minus 2, b equals 5, everybody. Now, and that works perfect. It's a simple geometric shape, but we are going to go with the fundamental theorem of calculus that says it's capital F of B minus capital F of A, because in case it's not a shape that we know the formula for, in which case the integral of 3, the antiderivative is 3x plus c. We don't need a c because we are evaluating it from -2 to 5. The c will go away. So plug in 5, plug in -2. So 3 times 5 minus 2, which is 3 times 7 equals 21. Both of them give us the same answer. What's the difference again? I want to make sure everybody understands. The difference is that this may fail sometime. Why would it fail? Because it may not be a shape we are familiar with. But this will always work, regardless. So this was completely a positive function, and it was area under the curve. But what happens if it's not? Evaluating integrals using signed areas. Use the signed area interpretation of the definite integral to compute the integral of -1 to 2 x dx. Well, we're going to go over the same concept. What is the function? Y or f of x equals x from 2, from -1 to 2. I hope you realize this is a line through the origin. And we want to go from -1 to 2. That means we want this area. And it's important to know, because this portion is above the x-axis, this area is considered positive, and this one is below, it's considered negative. So it's the difference of the two. Okay. If the function is positive, it's the area under the curve. If the function is not, it's the difference of areas. And each one, again, is a shape we are familiar with, is a triangle. Area is 1/2 base times the height. This point has coordinates 2, 2, which means this distance is 2. So is this one 1/2 of 2 times 2? That means the area for the green triangle is 2. What about the red one? This has coordinates -1, -1, which makes this distance as well as this distance 1. So 1/2 of 1 times 1 is 1/2. And this is considered positive, this is considered negative. So 2 minus 1/2 is 3/2. Again, not a big deal. It's a shape we are familiar with. We know the formula for the area. It works fine. What if it doesn't? We go to calculus. The integral of a to b f of x dx is capital F of b minus capital F of a. So this function is x. What is the antiderivative? 1/2 of x squared. So we're going to evaluate 1/2 of x squared from -1 to 2. First, we plug in 2, gives us 4. Then we plug in -1, gives us 1. 4 minus 1. So 1/2 of 4 minus 1, which is 3. So 3/2. Obviously, they are identical. What's the difference? This will always work. This may not be a geometric shape that we are familiar with, or we know the formula for the area. So what I want you to do as a practice, graph and use sign areas to show that the integral of -4 to 1/6 x dx is -45. Class, this is your function. These are the limits. Graph, and you should be able to come up with the answer in no time. Okay. Evaluate the integral of 0 to 1 x to the power of 7 dx. Obviously, this is using the power rule, so 1 over 8 x to the power of 8 from 0 to 1, and I don't write the constant because they go away. I plug in 1, 1 to the power of 8 is 1. I plug in 0, 0 to the power of 8 is 0. And 1 over 8 times 1 minus 0 is 1 over 8. And again, what I mentioned, here's the tip. Even if we use another antiderivative, capital F of x plus c over here, 1 over 8 x to the power of 8 plus a constant. In the evaluation theorem, because we're going to evaluate it at 1 and 0, the result will be the same. Why is that? Because capital F of b plus c minus capital F of a plus c, the c's cancel out. We get capital F of b minus F of a. So if I put plus c, because I'm going to over here subtract it, the c goes away. Now the integral of 1 to 2 x to the power of minus 1 dx. Notice x to the power of minus 1 is the same as 1 over x, and the answer is a natural log. And we're going to evaluate it from 1 to 2. It's ln of absolute value of x. Whether I put the absolute value or not makes no difference because the limits are positive. Both of them are 1 and 2. So obviously we know this is 0. The answer is ln 2, which is the exact answer, everybody. I'm going to repeat the question with different limits. And I'm going to write it again. Natural log of absolute value of x from negative 2 to negative 1. The difference is limits, even if one of them is negative, you have to keep the absolute value because ln of a negative number is undefined. It means nothing. So you have to keep it an absolute value. So this becomes ln 1 minus ln 2. And as you know, ln 1 is 0. So the precise answer minus ln 2. Don't forget, in calculus, we always come up with an exact answer unless they want an approximation. What about the integral of 0 to pi sine x dx? The derivative of sine is cosine, but the integral of sine is negative cosine x from 0 to pi. I keep the negative out. It makes it easier, and I would put cosine of pi minus cosine of 0. This is minus 1. Minus cosine of 0 is positive 1. So this becomes negative 2. And this changes it to positive 2 as the final answer. We're going to evaluate the integral from 0 to 2. So we are going to go with the basically power rule. This is 5/3 x cubed minus 4 halves because this is the exponent 1, right? So this is minus 4 halves x squared plus 2x. And of course, minus 4 halves is minus 2x squared. We're going to plug in 2. We're going to plug in 0. I hope you recognize if you plug in 0, you get 0. So plug in 2, and when we plug in 0, it results in 0, right? Because everything involves x. This is 8 4d-thirds. This is 4 minus 8 plus 4. This is minus 4 or minus 12 thirds. 4d-thirds minus 12 thirds. 4d minus 12, 28 thirds. The integral of 1 to 2, 4v to the power of 6 minus 3v cubed over v cubed dv. By the way, I'm using a variable that normally we don't use on purpose. It's important to know this variable and dv must be the same. So how do we deal with that? First, 4v to the power of 6 over v cubed is 4v cubed. Then this is minus 3. That's your first step, algebraic step. And I hope you recognize that this is a power rule. So this is number 3. You add 1, becomes 4. 4 over 4 is 1. V to the power 4 minus 3v plus 1 to 2. You plug in 2, and then you plug in 1. When you plug in 2, 2 to the power of 4 is 16 minus 6 or 10. This is 1 to the power of 4 minus 3 or negative 2. 10 minus negative 2 means plus 2 means 12. So pretty straightforward, everybody. The integral of 1 to 3 x squared minus 7x plus 2 over x squared dx. This question was done in the previous section, but without the limits. I hope you remember that. So you can use the answer and then evaluate it from 1 to 3. But I'm going to quickly go over that by making up 1, 2, and 3 fractions. The first one is 1, the second one minus 7 over x, and the last one 2 over x squared. Because I want to anti-differentiate, I'm going to change this to minus 7 times 1 over x, and I'm going to change this to 2x to the power of minus 2, so it becomes clear what we have here, everybody. This is x, this is minus 7 ln x, and this one, 2 over negative 2 plus 1, x to the power of negative 2 plus 1, which is minus 2 over x. We have done this before. It's in your notes. So plug in 3, plug in 1, and subtract them. When we plug in 3, we get 3 minus 7 ln 3 minus 2/3. When we plug in 1, we get 1 minus 7 ln 1 minus 2. And so let me start with this. This is 0, everybody. ln 1 is 0. So you have 1 minus 2, which is negative 1. So I'm going to repeat the first. I'm not going to change anything. And then minus 1 is plus 1. Now, we are going to keep this intact because we want exact answer. And we are going to add the rest of them. 3 and 1, 4 minus 2/3. 4 is 12/3 minus 2/3 is 10/3. And minus 7 ln 3, this is an exact answer. I can't emphasize this enough that why we want to keep an exact answer in calculus, okay? The integral of 0 to power 2, 1 plus cosine t dt. I hope you remember we did this before without the limits. In other words, we didn't have these two. So obviously, because of dt, the independent variable is t, so 1 becomes t, cosine becomes sine. Remember, the derivative of cosine is negative, but the integral is positive sine t from 0 to power 2. We are going to plug in power 2. That means power 2 plus sine of power 2. And then we plug in 0 minus 0 plus sine 0. Obviously, sine of 0 is 0, so this entire thing is 0. power 2, and sine of power 2 is 1. So you get simply power 2 plus 1. And you want to keep it that way because this is an exact answer, everybody. The integral of 5x squared of x plus 3 squared of x dx from 1 to 4. You want to evaluate this, everybody. Well, first and foremost, we're going to change this to x to the power of 1 half, which means the same thing here, right? And then this has exponent 1. And I hope you remember we did this one also. We are just evaluating it. So this has exponent 1 and 1 half becomes 3 halves. So 5 x to the power of 3 halves plus 3 x to the power of 1 half. And the reason we write them in this fashion because we want to make them ready for the power rule in essence. Okay. So what is this? 5 divided by 3 halves plus 1, x to the power of 3 halves plus 1. What is this one? 3 over 1 half plus 1, x to the power of 1 half plus 1, and evaluate it from 1 to 4. Okay, let's choose a color. So this is 5 halves. This is 3 halves. This is also 2. Now, plug in the upper limit 4 and evaluate it. Plug in the lower limit 1 and evaluate it. The difference is of interest to us. So please understand, this was the only calculus step. This was algebra. This is also algebra. You just evaluate it. So when we plug in 4 to the power of 5 halves, for example, means square root of 4 to the power of 5, 2 to the power of 5 is 32. Their product is 64. 4 to the power of 3 halves means the square root of 4 to cubed, which is 8. 2 times that is plus 16. And of course, this is 1, this is 1, this entire thing is 4, so minus 4, and the answer is 76. This is from the exam review. Water flows from the bottom of a storage tank at a rate of R of t equals 200 minus 40 liters per minute. Find the amount of water that flows from the tank during the first 10 minutes. This is known as the net change theorem. If capital R of t represents the amount of water that flows from the tank at time t, then the rate of flow is given by capital R prime or lowercase rt equals 200 minus 4t. Therefore, the amount of water that flows from the tank follows what we call a net change theorem, the integral of a to b f of x dx, which is capital F of b minus f of a, is also known as accumulated change or net change. So therefore, the amount of water that flows from the tank during the first 10 minutes is this integral from 0 to 10, and you put the function r of t. This is 200t, this is minus 2t squared. You plug in 10, you plug in 0. When you plug in 0, obviously becomes 0. That's why we have this part 0. But if you plug in 10, this is 2000 minus 200, 1800 liters, because this was liters per minute. So liters. That was a rate. Many fish grow in a way that is described by the von Bertalanffy growth equation. For a fish that starts life with a length of 1 centimeter and has a maximum length of 30 centimeters, this equation predicts that the growth rate is 29 e to the power minus x centimeters per year, where x is the age of the fish. How long will the fish be after 4 years? Rounded to 1 decimal. So what's going on? The growth rate, the derivative is given. So if that is the rate of growth, then L of x, let L of x represent the length of fish at age x, and the growth rate would be the derivative of that, L prime or dl dx equals to this 29 e to the power minus x centimeters per year, where the initial value L of 0 is 1 centimeters. Okay, so it's very important to understand that. Quick recap. So we let L of x represent the length of fish. So this would be L prime or dl dx, 29 e to the power minus x centimeters per year, with the initial value L of 0 equals 1 centimeter. So the amount of increase follows the accumulated change, the net change theorem. So the amount of increase for the first 4 years would be the integral of 0 to 4 of this rate function. This is the amount of increase. And the answer is itself, you divide by -1, so minus 29 e to the power minus x, 4 to 0, from 0 to 4, so you plug in 4, you plug in 0, and it becomes, we take the -29 out, it's easier, e to the power minus 4 minus e to the power of 0, this is 1, but nevertheless, you have to put it into a calculator, and I'm going to write it with a bunch of decimals. This is the amount of increase, but L of 0 is 1. That means we have to add it. And then since they want 1 decimal, look at number 4. Next to it is 6. It goes up to 29.5 centimeters. This is one way to do that, everybody. However, the second method, and I'm going to discuss it in a moment, if they ask you how long is the fish after 4 years, 5 years, 7 years, you have to repeat this again, this integration. Instead, let's find L of x without paying any attention to the limits. Since we know this is the answer, we're going to add a constant, and of course, L of 0 is 1. So if we plug in, replace the x with 0, then L of x becomes 1. This is e to the power of 0 or 1, negative 29 plus what number is 1? That must be 30. Replace the c. Now, the advantage of this is, at this point, I'm going to plug in whatever they ask. After 4 years, I'm going to plug in 4, and it gives me the same thing. But if, let's say, part B says, how long is the fish after 7 years? Then here, I'm going to replace the x with 7, so on and so forth. This makes it easier, everybody. I want to look at another example similar to what we just did. The rate of increase in a bighorn ram's horn length has been modeled by this function. F of x is 0.1762 x squared minus 3.986 x plus 22.68 centimeters per year for x between 3 and 9 years. Find the accumulated change in a ram's horn from age 3 to age 9. So, of course, we are using this accumulated change. The integral of a to b f of x dx is capital F of b minus capital F of a, also known as accumulated change or net change theory. Now, let capital F of x denote the length of a bighorn ram's horn at age x years. Then the accumulated change in capital F of x over the course of 3 to 9 would be the integral of f of x dx from a to b from 3 to 9. So we're going to take the integral of this one, of course, times dx from 3 to 9. The integral of a to b f of x dx, the integral of 3 to 9, and you put this function here. So this becomes 0.1762 divided by 3x cubed minus 3.986 divided by 2 because x to the power of 1 x squared, and this is 22.68 x from 3 to 9. Now, of course, you need a calculator because it's tedious a little bit if you want to do it by hand. You plug in 9, cube it times this, divided by 3, 9 squared. You plug in 9, you plug in 3, and you evaluate it, and it becomes 85.5036 minus 51.6888. The result is 33.8148. And the units, always you have to answer with the units. The units are in centimeters. Accumulated change or the net change theory.